So thank you, and I'd like to turn this over to both Judah and Xiangdong, the co-chairs for our working group on Arctic change and the possible influence on mid-latitude weather and climate. So thanks for tuning in, and I think, Judah, you're going to go first, right?
Yes. Yes.
Great.
Thank you, Kristen, for the introduction, and thank you, everybody, for joining. So we held a workshop early in February on this topic of Arctic mid-latitude linkages. A lot of lively discussion, and so we're going to summarize some of that today. I'll talk about mostly focus on observations, and then Xiangdong will follow up with mostly his emphasis on modeling and modeling experiments. So we had 6 organizers, I think, of the workshop. Their names are listed here. Myself, Xiangdong, was Jennifer Francis, Thomas Young, Ron Kwok, and Jim Oberlin. Okay, so we start off this workshop talking about Arctic amplification, and even though it is something that is predicted by all of the models, and something that was anticipated as a consequence of global warming, it turned out that it wasn't as simple as you might think. So it certainly starts off with the idea that a diminishing cryosphere, melting snow and ice, will lead to lower albedos and great absorption of solar radiation. And certainly, if you look at the trends in sea ice, is here's the slope of the trend in the September sea ice, and here's some also pictures from March and September of the sea ice concentration across the Arctic basin. And again, you all know this, that the sea ice is melting, in particular in the late summer and the fall. You get the greatest decrease in sea ice, and you can see here on the Chukchi and Beaufort seas are really the large decreases. And then again, you have that in the winter, but we'll get into much more detail about that. So here I've also, but it's not just sea ice, there's snow cover is also involved in this story, and so I've plotted here September sea ice and the June northern hemisphere snow cover, which is in red, and the sea ice is in this darker blue, and you can see that the June snow cover has been decreasing, and in general, the summer, and there's not really, it's spring, and even maybe a little bit in summer, there's not too much past June of snow cover, but it's been decreasing at a rate at least as much as that of the September sea, the late summer, early fall sea ice. So that it's not just sea ice that's contributing to these lower albedos, but also the decrease in the snow cover. But I think also part of the story is what's happening in the fall snow cover, fall and winter, but especially in the fall, and there's been this pretty robust increasing trend in the fall snow cover, and this is not, it's true for the northern hemisphere, but in particular over Eurasia, which is mostly in Siberia, in this month that I'm showing of October. Okay, so certainly with this idea that less sea ice, more absorbed solar radiation, you're getting this amplified warming in the Arctic, and here's a couple examples of showing that. So this is showing the global and Arctic temperature trends. So these lighter grays are the global temperature trends for the different seasons, and then you have the Arctic trends here in the darker black, and just the point made here is that you can see that the Arctic temperature trends are increasing much quicker, or of greater magnitude anyway, of greater amplitude than the global trends. And here's showing it with on a latitudinal and vertical plot. And so looking at the winter, you can see, so starting, let's say, maybe from the tropics and going poleward, you can see there's this acceleration, or this greater magnitude of warming as you get closer to the pole, and so that's what we refer to Arctic amplification, where it's weaker, certainly in the mid-latitudes, and then it gets greater as you get towards the pole. And it's not I'll show this again further later. But it's not just at the surface. I guess this Arctic amplification is greatest in the fall, and here's the fall, and here's the winter, and then less so certainly in the spring. But it's at a minimum really in the summer months. And these plots are courtesy of Fred Lilliberte and Lawrence Murdoch, Fred Lilliberte attended the workshop. So, but it turns out that reasons for Arctic amplification are more complicated than the community realized. And actually, sea ice loss is not the biggest contributor to Arctic amplification. And you can see here, so there's albedo, but I think it turns out in this paper, what they refer to as lapse rate was the biggest contributor. But there are other factors. There's downward long-wave radiation, and then there's water vapor and clouds. So it's not just a matter of what's contributing to Arctic amplification is more complex than just a change in albedo. Okay, so like here's an example. So that's I think was presented at the workshop. So on the left we have the sensible heat flux, which is what you might expect to come. Well, I mean it's not an albedo, but maybe but its impact this would be the impact that you would see from a loss to sea ice. You would increase of sensible heat flux from the ocean into the atmosphere, and then on the right side is the impact from, or at least the trends in increasing energy from that is downwelling long-wave radiation. And at least in these plots presented here, and then in this analysis, you can see that the contribution to the warming trends or this increasing energy at the surface is much greater from the downwelling long-wave radiation than it is from sensible heat flux. Okay, but regardless of what's the causes of Arctic amplification, or certainly maybe there are these implications from the causes from the amplification, what are the impacts from this Arctic amplification? So one thing that was discussed quite a bit at the workshop, and that's where most of the research has been focused on, looking at these Arctic mid-latitude linkages, is this what's referred to as this warm Arctic cold continent, or sometimes it's called cold Eurasia. So I think one thing that's important to point out, so here's the change in the polar cap heights, which is certainly dependent on temperature. This was from the most recent year, 2016, and you can see that there's warming or this increasing or dilation in the geopotential heights throughout the year, but it's not isolated. It's not limited to the lower troposphere or in the boundary layer. It's certainly getting up to the tropopause, and at times it's even making it into the stratosphere. And if you look at the trends, so over this era of Arctic amplification, which I'll show in a minute. That warming is, again, really not confined. It's almost consistent. It's constant throughout the year, but it's not limited to the near surface or the boundary layer or even the lower troposphere. And the fact that it can get up to the jet stream level, I think certainly lends this plausibility that it can be impacting the jet stream and then therefore mid-latitude weather. So if you take the temperature trends, these longer temperature trends, you get this pattern that you expect, that's been predicted by the models, that you get warming throughout the entire hemisphere globe. Here I'm just showing the hemisphere, and then you get this accelerated warming, or this Arctic amplification of the warming. So I'm just showing here for the winter season. But if you look at the time series and you separate out the Arctic from the rest of the hemisphere, so the Arctic is in red and the rest of the hemisphere is in black, starting 1960, the trend in the Arctic temperatures was similar it was comparable to that in the rest of the hemisphere. There was greater variability, but the trend was similar. And only since about 1990 do you really see this divergence or emergence of this Arctic amplification. And then if you take the temperature trend over this period of what we call now Arctic amplification, you get a more surprising result where you get warming, again, even greater accelerated warming in the Arctic, but now in the mid-latitudes you have this cooling. And if you look at the latitudinal temperature trend, you get warming in the lower latitudes in the tropics. You get accelerated warming in the Arctic, but you would get this cooling in the mid-latitudes. And so are they linked? Is this Arctic warming linked to this mid-latitude cooling? So there have been quite many ideas out there. One idea, maybe the one that's gotten the most publicity and caught the media's attention the most, is this changing of the large-scale planetary waves in the atmosphere, where Arctic warming causes the slowdown in the jet stream, but also causes the poleward side of these waves to become of greater amplitude, and so you get slower, larger moving waves, and this can lead to maybe increased blocking and more extreme events. But I think most of the studies have, recently, again, I think more and more studies have looked at a possible stratospheric pathway, certainly in the winter time. And this is, kind of the schematic that we made for snow cover, where you have increasing snow cover that leads to this a regional perturbation, which is so if you have positive snow cover anomalies, it leads to increased blocking, Euro blocking, or a strengthened Siberian high. They're pretty much the same thing, but discussed different, named differently in different studies. And then that is conducive to leading to more energy propagation into the stratosphere. That leads to a weakening of the polar vortex or sun stratospheric warming, and then there's downward propagation that leads to a equator shifted jet stream, more cold air outbreaks, more snowstorms, and often has projected onto the Arctic Oscillation, though recently that has not been the case. And this same kind of pathway through the stratosphere that was put forth with snow cover has been increasingly adopted by sea ice. Here's just an example of one paper, it's Kim et al. Paper, and they also you could see that you get this increasing blocking at high latitudes initially that leads to this sun stratospheric warming, and then this downward propagation, you would get this type of negative AO, and they show this both in the observations and in the models. But very, very similar, and you can see here, you should be able to see here, this Euro blocking or this northwestward expansion of the Siberian high here showing up in the observations and also in the models, but weaker. So, and that is what's been really considered the most, at the workshop, the consensus was that the most robust relationship that's coming between the Arctic and mid-latitude with ones, if this relationship exists, is this strengthening or increasing Euro blocking, close to this Barents-Kara Sea region from the sea ice loss there, and then this leading to downwind or downstream cooling across Eurasia. And again, this shows, this was in a review paper, kind of synthesis of both snow cover and sea ice. But again, you get this either way, whether you get increased snow cover or decrease in sea ice, you get this increasing Euro blocking, which then has been shown to be very favorable for exciting wave energy to escape from the troposphere into the stratosphere, leading to this a weakening of the polar vortex and sun stratospheric warmings, and then you get this maybe strong warming over the pole, but there's downstream cooling over the Eurasian continent, but it can be also North America, but certainly the most robust result, the one that's statistically significant, is the one over Eurasia. But there are certainly a lot of challenges, and a lot of the ideas about Arctic mid-latitude linkages have come from the observational analysis and less so from the models. But there's a lot of challenges. So in in the Arctic, there's a scarcity of observations. Also, we have a short time series, so especially if you're just limiting yourself to the period of Arctic amplification, which is since 1990. But it's not just the observations that have shortcomings. There are no model deficiencies. Until now, there have been really uncoordinated modeling studies, so a lot of times we're comparing apples and oranges. So they're not similar, and they've given very divergent results, which Xiangdong will touch on in his part of the talk. There are a lot of biases in the metrics that we use. I talked a little bit about blocking indices or the wave amplitudes, and that is also very subjective. And of course, there's large natural variability in the system. The climate system is complicated. So just touching on very quickly on some of those challenges. Here's showing station observations in the Arctic, so there's maybe more on the land, represented by these black dots, but buoy ocean observations, they're very far and few and far in between in the Arctic. So it's a lot of scarcity of observational data. And again, this idea that there's a large natural variability is complicated. So there's, you could say there's Arctic amplification influencing mid-latitude weather, but how do you separate that from other things that are going on? Natural variability, there's polar vortex, there's change in the cryosphere, separate from even Arctic amplification, and there's just the larger picture of global climate change. All right, so I'll leave it there and pass it off to Xiangdong.
Okay, hello. Hello?
Hi, Xiangdong, we can hear you.
Oh, can you hear me?
Yes.
Yeah, so I'm going to present. After that, there will be questions, answers, right?
Yes.
Okay. Yeah, I'm going to following Judith's talk. He says the climate system is very complicated. The observational record is short, so there's a larger amount of modeling studies. So currently, I'm going to present some examples of modeling study, and including progress and the challenges. So this modeling experiment shows the relationship between Arctic warming and mid-latitude cooling. So the research team employed the GFDR model. They enlarged the SST north of 70 degrees to look at the impacts of warmed SST on the surface air temperature. So they did regression analysis between the surface air temperature over the Chukchi Sea and over the Barents Sea and the Coral Sea with the northern hemisphere surface air temperature. They found there is a relationship between Eurasia cold temperature and North American cold temperature with this Barents Sea Coral Sea warming. They also they did a similar regression analysis using the surface air temperature of the Chukchi Sea and the East Barents Sea as the index, and also did the regression analysis. They found the negative correlation, that's cooling over North American. Okay, and then they applied the same regression analysis to all the CMIP file model simulation results. So they found the most models shows a negative regression coefficients. The multi-model ensemble mean shows a negative value here. Is a support observation study. That means when Arctic warming, there's a cold temperature over the mid-latitude Eurasia and North America. However, when we look at the other modeling study, that has been done by Environmental Canada group. So they conducted 50 ensemble simulations, and then they first look at the changes of sea ice over the Barents Sea and the Coral Sea. So they found that there is all the members shows a decrease of the sea ice cover in this area. So multi-model, multi-ensemble, not multi-model ensemble mean shows a decreased rate of the CIS close to the observational one. So that means the model supports the observed CIS decrease in this area. However, when we look at the surface air temperature over the Eurasia, they found that there is all model ensemble runs shows an increase of surface air temperature. And then they did analysis, regress the surface air temperature onto the CIS over the Bering Sea and the Coral Sea. They found that there is a slight decrease of surface air temperature, but the magnitude is much smaller than the observed one. And then based on this study, modern study, they conclude the Eurasia cooling temperature during recent decades may not be related to the Bering Sea, Chukchi Sea CIS decrease. So we can see there's a difference, different results across the different model simulations. So there's a challenge. Okay, in addition to simulating temperature changes over the Arctic and the mid-latitude, all the modeling studies also look at the dynamic physical process that can be responsible for the changes of temperature over the Arctic and the mid-latitude, and also look at the linkage between them. Here I would like to present two examples. Actually, Judy already showed the first study. So at the workshop, we discussed a number of different pathways to potentially link Arctic warming or CIS retreat and the mid-latitude weather and climate. So one pathway is through interaction with the stratosphere. So if there's a decrease of the CIS or warmed ocean over the Bering Sea and the Chukchi Sea, they can trigger planetary wave propagate upward to the stratosphere, and then there's a downward propagation of waves that will change phase of Arctic oscillation from a positive to the negative phase. There's other pathway. So through stationary Raspberry wave propagation within the troposphere, so finally they can change the phase of Arctic oscillation. So Arctic oscillation, the phase change of Arctic oscillation is critical to cause to link Arctic warming and the mid-latitude cooling in those studies. So however, when we look at all the model simulations, so different models shows a different dynamic response. So this is a summary by Doug Smith that presented at the US CLIVAR workshop in February. So we can see some models shows negative Arctic oscillation or North Atlantic oscillation. But the other model results shows a positive or enhanced positive phase of Arctic oscillation or North Atlantic oscillation. So we can see there is a larger uncertainties. A different model shows a different dynamic response. So this remind us to think about if Arctic oscillation or North Atlantic oscillation is really dynamic linkage between Arctic warming and mid-latitude weather and climate. So actually, we did study, circulation study back to some year. Oh, okay. First, we look at if Arctic oscillation or North Atlantic oscillation really change temperature similar or the same as what has been observed in the real world. So we split the time period to one period, the early period from 1958 to 1996, and then after that year. And then we look at how Arctic oscillation changes the surface air temperature. So this is the regression analysis results. We can see there is a warm temperature anomaly of the Eurasia. That's a cold temperature of the Greenland. So when we compare these regression results with the linear trend during the same time periods, it's quite similar. That means the positive phase during this period, positive phase of Arctic oscillation during this time period can well explain the surface air temperature linear trend. But however, we look at the later time periods, the Arctic oscillation mainly stay in the negative phase or neutral phase. So The regression result shows a cooling of the Eurasia, but a warming of the Greenland area. But there is no strong amplification signal within Arctic domain. So this is quite different from a linear trend from surface air temperature analysis. So this may suggest the Arctic oscillation-driven temperature changes may not well explain the recent potential linkage of Arctic warming and the mid-latitude climate cooling. So this reminds us to look at the circulation dynamics analysis. So actually, some years ago, we did the circulation analysis to look at why there is acceleration of Arctic climate system changes. So we found there is a dramatic spatial pattern, spatial structure changes of atmosphere circulation. So we can see in the early years, in 1980s, it's mainly the circulation pattern, mainly dominated by Arctic oscillation with the three centers of action. But in the later years, this spatial structure changed to this dipolar structure with the one center of action over the Eurasia and the other center of action over the Aleutian area, North Atlantic storm track area. So corresponding these changes, we found that there is acceleration, rapid changes of Arctic system. So we give the name of this pattern as Arctic rapid change pattern. So what this pattern may cause for the energy budget, we did the energy budget analysis. Here I would like to give an example showing here. So we found that when the Arctic rapid change pattern went to the negative phase, there is enhanced warm air and moisture air transport into the center of Arctic Ocean. And then we extend the time series of the ARP pattern to the most recent years. We found that after mid-1990s, there's an increased frequency of occurrence of this ARP pattern to the extremely negative phase. So corresponding to this extremely negative phase, there's a dramatically increase of surface air temperature over the Arctic, but there's a cooling over the Eurasia. So this changed pattern, spatial pattern of the atmosphere circulation, will explain the recently amplified warming of the Arctic and also cooling of the Eurasia. So this is a consequence of changes of heat transport. Let's look at this figure again. Okay, from this figure we can see there's enhanced warm air transport into the Arctic, but the polar air is circulated to the mid-latitude to cause cooling over there. Okay, actually, when this paper was published, we looked at all the model simulations, including CMIP3 and CMIP5. So most models cannot simulate its extremely shifted spatial structure. But there's a good news. So at the beginning of this, it's in the last month there was a workshop in Aspen. So there's some new modeling studies. So they found there's the emergency of this pattern. So the new modeling study already identify these dipolar circulation changes. So we can see there is a center of action over the North Pacific, and also there is a center of action over the Eurasia. So under the circulation changes, the circulation pattern changes, that's a warm the Arctic and the surrounding coast area, that's a cooling of the Eurasia mid-latitude. So as we can see from previous slides, so there's a diversified modeling results, not only for temperature change itself. There's also diversified results for dynamic studies, the circulation studies. So at the US CLIVAR workshop, we had extensive discussions about how to coordinate modern studies to identify robust, solid signals that can be support or not support the hypothesis there will be linkage between Arctic warming and the mid-latitude. So following that discussions, there has been proposed the MAPLE project. We call it a polar amplification multi-model intercomparison project. So there are a number of planned modeling experiments. The first group is similar to the AMAP modeling experiments. So the control experiments will be forced by present-day climatological SST and CIS. And then there's a different sensitivity experiments. So we change S, for example, for this subgroup of sensitivity experiments, we use a pre-industry SST to force model. And we use SST in the future 2-degree warming climate to force model. And then we are going to make a multi-model and a multi-model ensemble comparison with the control runs. We try to identify if there is a solid or a robust signal. Similarly, we are also plan to do the CIS sensitivity experiments and over the Arctic and Antarctic. There are also 3 other groups of experiments. Here I just show other, because the time is limited, I just briefly show the other groups experiments using fully coupled model. Because recently we had many discussions about the fully coupled interactive ocean CIS atmosphere interactive process. The ocean atmosphere interaction may amplify the signal forced by CIS anomaly. So in the future MAPLE project, we also include these fully coupled experiments. If you want to learn more about this MAPLE project, so maybe we are going to publish a paper about this, and maybe you can read the paper in the future, or if you have questions, maybe we can have a discussion after this presentation. Okay, here is the summary. So we found that there is no agreement has been reached among the modeling studies. So there's also uncertainty about the dynamic processes. This will influence the selection of metrics to evaluate dynamic model performance. So there's also uncertainties about the prescribing forcing. At the US CLIVAR workshop, we found some models shows a positive heat flux from ocean to atmosphere, but other model shows a negative heat flux from atmosphere to ocean and CIS. So we can see there's uncertainties about that. So we also don't have enough amount of studies about model systematic bias and its impacts on the signal we identify from the model simulations. So finally, we have proposed coordinated model experiments. So the name is PA-MAP, Power Amplification Multi-Model Intercomparison Project. So we are still coordinating all the modeling groups to move forward. Okay, I'm finished here. Thank you.